Hi, this is going to be the review slides for the for exam one for organic two, something like that. So we're going to go ahead and get going on this. I have made the corrections. I know there were some typos and things like that from the on the slides, so they have been corrected, and I'll get those uploaded. I've also made a very slight change to the slides, and those will be incorporated in too. Stuff like that. So we'll go over these. So if we're interested in the hydrogen atoms for the unrelated, or figure out if they're unrelated or homologous and antiotopic or diastereotopic, right? So you got the molecule. There's going to be dark arrows pointing to the hydrogens of interest, stuff like that. So actually, what we did when we came up with at recitation on Friday, again, a reason why you should come to recitation, actually came up with this sort of decision tree for figuring out what they are. So if you look at it, so you take, so what you do is for the two hydrogens of interest, what you do is make two new molecules where one of the hydrogens is replaced with something different, say fluorine. I usually do fluorine just because, why not? But the first question you say, if you were to name the molecules, would they have the same name? If they don't, then those hydrogens are considered unrelated. But if they are, then you have to ask the next question is there a new chiral center created, right? So remember, a chiral center is a carbon with four different things attached. It could be other things. Usually it's carbon. Has four different things attached. If it doesn't, if you haven't made a new chiral center, then those hydrogens are considered homologous. Okay, but if they are, so then you have to question is how many chiral centers does one of the molecules now have, right? If the molecule only has one chiral center, like the one you just created, then it's considered an antiotopic. If the chiral center now has two or more, right? Then those hydrogens are considered diastereotopic. So this is sort of the decision tree you sort of have to go down, and this is included in the new set in the updated slides. Okay, so let's see. Let's go with this. Thanks. So antiotopic. Okay, so what do you do? So first thing to do is to go into try to get this. Hold on here. Try to make it so it's not quite so. There we go. Now you can see the slides. Okay, so what you do, right? So the hydrogens of interest are here, right? So you come in and you say, okay. I'm going to make put a fluorine on one side, or for one of the hydrogens, and then make another molecule where the fluorine's on the other. So it looks like that. There. Okay, so now the question becomes, would it be the same? Would it be the same name? Yes, it would, right? So it does. So, because they're hanging off the same carbon. So they're at least homologous, right? So is there a chiral center here? Well, yeah, there is actually. So then, right, we don't have to work with one now. So, right, because there's a CH3 there, right? Stuff like that. So, right, so there's a fluorine, a hydrogen, a CH3, and then this big thing right here. So there's at least one chiral center there, right? And is there a chiral center in the other rest of the molecule? Well, there's not, right? So there could be one right here, right? But both of these are CH3s coming off of this carbon, that carbon there. So there's not one. So this would end up just being an antiotopic because there's only one chiral center, an antiotopic. Okay. So there's only one chiral center in the molecule. Okay. Something like that. So, okay. So here we go. So here's the next one, right? Do the same thing. Right, so fluorine, hydrogen, right? H, right? You try the other one, right? So we have H and then fluorine, right? H. Okay, so would they have the same name? Yes, they would. So like that. So right, because the hydrogens or the fluorines are on the same carbon again. Right, so now is there a chiral center? Well, you say, is there four different things, right? So remember back, right? So fluorine, hydrogen, right? These are both CH2s, right? CH2. Well, there's a tie, and then you go out one further, right? So this is a CH2 over here, and then this is just a CH, right? So this side is different from that side, right? So there's a chiral center there. Okay. Okay, but what we've done is we've actually created a chiral center here as well, right? Before there actually wasn't, right? Because this side, these two sides are the same thing, right? CH2, 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 right? You go around, it's the same. So so there's not a chiral center here, but now there is, right? Because we've sort of made this side different than that side, right? So now there's a chiral center here, right? If you want to go to the progressions, right? So it'd be right CH2, CH2, and then CH2, and then this thing with a fluorine on it. So again, the side's different, right? So since they're different, this is diastereotopic, right? Okay, so now for this one here, right? So put a fluorine over there, right? Oop, gotta get that bromine. Okay, so again, would these have the same name? Yes, they would, right? But right, and again, we've created a chiral center here, right? Because it's a CH3F H, and then this thing, right? But there's also another chiral center here, right? Because there's a hydrogen there that's understood. There's a CH3, right? There's a CH3 here, H, Br, and then this massive thing, right? So since these are both, there's two chiral centers, they're, again, diastereotopic. Okay? So if you had something like this, right? Right, so if you had a hydrogen here and a hydrogen here, right? So, right, so again, you would pick this out, right? Put a fluorine there, the hydrogen there. Hydrogen here, fluorine there. Now, they are, right, so what would this be named, right? It would be, right, this would be 1, 2, 3, 4, right? So it's 1, 2, 3, 4, so it would be a butane, so it would be 1 fluorobutane. But this one here would be 1, 2, 3, 4. This would also be a 1 fluorobutane. Okay, so they at least have the same name, but did we create a chiral center? No, because remember there's two hydrogens here, right? So that can't be a chiral center. So this would be homologous. Right? And if I said, right, so if I had a hydrogen here and a fluorine there, or excuse me, hydrogen there, right? We're interested in those two. Get ahead of myself, right? So if we put a fluorine there and a hydrogen there, put a fluorine there and a hydrogen there, right? Again, so here the numbering would be 1, 2, 3, 4, right? Because the numbering here would be 2 fluorobutane. Here, the numbering 1, 2, 3, the numbering would be 1, 2, 3, 4. This would be 1 fluorobutane. So these are considered unrelated. Okay, so some extra ones for this. Okay, so be careful. So. Okay, now this one I've changed to look more, to mimic more of what you would see. Okay, on here. So circle the molecule from the pair that corresponds to the IR spectrum. This is how you're going to see it on the test. Okay, so this one, right? So here's the IR spectrum. So you need to figure out which one of these, right? So both of these, right, would have CC and CH bonds, right? This would be CC and CH bonds, right? Okay, but that's all this one would have, right? But this one would also have, and I'm going to give you this chart, right? So it's going to have this one here. So you're going to have you would also have that, the C double bond C, and the hydrogen CH such where the hydrogen or the carbon's on a double bond here, right? So this one would be what? This one's in the 3020 to 3100 range, and this one is in the 1640 to 1680 range, right? So that would, so the 1650 would fall right into that range. This one here would fall right into the range. So this is the one we're interested in. Okay. Now for this one, again, we're going to look at our IR chart, right? So this one, right? So they're always going to have the CC and the CH bonds, right? Oops, CH. Okay. Now the question is, what else is this going to have, right? So this is going to have also the C triple bond C, and the C and the right? So we're going to have that, the C triple bond C, and then the CH bond where the C is attached to an alkyne there. Okay, but this one here, we're going to have this C triple bond N peak. Okay, so the C triple bond C, when you come onto your chart, it's between 2100 to 2260, right? And then this one would be at 3300. Okay, this one here, right, is down here, right? It's 2100 to 2260. Now this peak, right, becomes between both right between these two, right? We cannot tell from this peak if it's here or here, but we have to look at what's not only what's there, but what's missing, right? If we had this molecule, right, we would also need to have this 3300 peak, right? We don't have that, okay? So here's our molecule. So that would correspond with that one there, because we're missing this peak here, okay? But again, I'm going to give you this chart, right? You're going to need to just know how to use it. Okay, next up, predict the structure. Okay, so for this one, I'm going to give you mass spec and IR information, right? So with that, so for here, first thing to do with this is to just look to see what this is. Okay, so it's 1730. So you come down here, and it's an aldehyde. Right, so you just look at this chart. First thing you should do. Okay, and then you're right. So what that means is that this mass is not just C plus H, right? It also includes an oxygen in there, right? Because the only way you can have an aldehyde, right, it's going to have that C double bond to O, right? So what we need to do is to figure out what the C and the H is, right? What those add up to is you have to subtract the oxygen from this mass, right? So this is what, 42, right? So like that. So this is our C plus H, right? Okay, so here we go. So so if we had 2 carbons, right? So remember this whole for every 1 carbon, the maximum number of hydrogens you can have is 2n plus 2, right? So if we have 2 carbons, right, that means that the max number of hydrogens, right, would be what? 2n's, right? 4, it would be 6, right? So that would mean the maximum mass is 2H6, right? So that's 2 times 12 plus 6 times 1, right? So that would be 24. So this would be 30, right? Well, that's not enough, right? So here we go. So we're going to do three carbons, right? So the maximum of hydrogens, right? Max H would be what? It'd be 8, right? So 6 plus 2, yeah, 8. Okay, so C3H8, right? So that would be 3 times 12 plus 8 plus times 1, right? So it's 36 plus 8 would be 44, okay? But ours is 42, right? So that means that we're going to have to subtract 2 hydrogens, C3H6, right? So that's what we know what that is. So our final formula, right, so is going to be C3, right, so because we needed to remove 2 H's, right, so C3H6, O. This is going to be our final formula. Okay, so when all of these things go, right, first thing you do is to DOU, right, so 3 times 2 plus 2. We don't have any nitrogens, we don't have any, right, so no nitrogens, no nitrogens, no halides, right, plus 6 oxygens, right, so it's 6, right, so it's 8, oop, I'm sorry, this needs to be an 8, minus 6 minus 8, 2, it's 2 over 2, which is 1, okay, now, where is our, so this means rings plus double bonds, right, so we know where this is, right, we know there's a, what this is, because remember this, the aldehyde, right, is C double bond there, there's our degree of unsaturation, right, the C double bond to O, okay, so that means you can't have a ring, right, and so for this, right, it's going to have to be CH2, right, so there we go, that's our structure. Remember, we can't do this, right? That would correspond with this. But remember, we have an aldehyde in here. This is a ketone, right? So we can't do that. This is our structure because aldehydes have to be at the end. Okay, next up. Now for this one, I don't think I give you the IR spectrum for this one. I just think it's the NMR. So, but that's okay. I think you'll be okay without it. So you should be just fine without it. So, but in this particular example, I'm giving it to you. So let's go over it. Right. So CH, or see, so if it's over 3,400, it could be right. It could be right. So it could be the CO, or it could. I'm sorry. It could be the OH or the NH, right? But we know it has to be the OH, right? Because we don't have any nitrogens, right? That's our formula, right? So this is going to be an OH, right? So we know have an alcohol, so good, right? So the 3050, and then the 1650 corresponds to, it's the 1100 that corresponds with the CO, okay? These guys here, the 3050 and the 1650, correspond to double bonds. Okay, so this is the 3050. That's the H coming off of a double bond, and this one is the C double bond C. Okay, so we have that information there. Okay, so what else do we know? Okay, so if you think about what carbon NMR is, right? So the decoupled ones, right? It's going to show you all of the peaks. Okay. And then the depths 90 and 135 are going to tell you what kinds of things there are, right? So if there's C, CH, CH2, CH3, okay? So depth 90, right? This only shows a CH, right? So that means the 138.4, right? That's our CH. That's a CH, okay? The depth 135, the positive does CH and CH3, right? So we already know that this is a CH, right? Because it would be listed up here. Okay, but so we don't have any, so no CH3s. Okay, otherwise it would be listed here. Okay, now the rest of these 1, 2, 3, 4, 1, 2, 3, 4. The rest of these are CH2s, right? Because that's what the negative shows you. Okay, so the rest of these are CH2s. Now notice what else we have. We also don't have any just C's with no hydrogens on them. Okay. So from there, right, you can look at the chemical shift chart. So look at the carbon-13 shift chart, right? So you look here, and you say the 30 region, which is right around in here. This is sort of normal, especially for CH2s, right? There's probably not a whole lot going on. You could have a halide, but we don't have a halide up here, right? So these guys here are probably just going to be regular CC bonds. Okay. This guy here. Right? So 60, in the 60 range, right? Right. It can't be a halide, right? Because we don't have a halide in the formula. It can't be a CN, right? Because here, but the shift would indicate that this has an O on it, right? So it's a CH2. So this is a CH2, right, with an O, but we know that there's an alcohol, so it's an OH. But notice how you have a CH2 OH. Well, the only way, right? So if I write it like this, right? What does that mean, right? There's only one attachment point, right? So that means that this is going to have to be at the end, at some sort of end of the molecule, right? Okay, so what about these guys here? So 114, 138 here. Again, so they're sort of right in this range, right? So they're not CN bond, right? C triple bond N, right? Because we don't have any nitrogens. It's not an aromatic, right? For aromatic, it would need to be like a benzene. We only have 5 carbons, so it can't be that. So C double bond C, that's probably what it is, right? So these guys here are C double bond C, right? But again, notice how we have a CH2, right? CH, right? Here, let me draw those out. H. Notice again, all 4 bonds on this carbon are accounted for, right? 2 hydrogens and a double bond. Again, this means this guy is at the end of the molecule, okay? The attachment point is right there, okay? And so what else do we have? So we have this taken care of, this guy, and this guy, and the only thing we have left are CH2s, right? Because we knew that from the depth 90, right? So this is at one end, this is at the other. Oh, the other thing, I can't believe I forgot this. You know what? One thing you also want to do is a DOU. I can't believe I forgot that. 5 plus 2. No nitrogens, no halides, right? So minus 10, 2, right? So 12 minus 10, 2, 1, right? Aha! It makes sense, the C double bond C, right? So it's at least a linear, right? So the final structure, right? So then we have a CH2, right? A CH2, right? From these two that are accounted for. But again, those have 2 attachment points, right? So those are your pieces, right? So the final structure for having all of this make sense is CH2 with an alcohol on it, going to another CH2, CH2, CH, right? It's going to attach here, double bond CH2. So there's your final structure. Now, does this make sense, right? So a CH on a double bond, right? That's what the couple, a CH and a CH2, right, on a double bond, right? 2 CHs, right, with not much attached to them, and then a CH2 with attached to something electronegative, like the alcohol. So there you go. There's your final structure. Like that. So. Okay. Now, last one's hydrogen NMR. So this one, okay. So predict the structure. Okay, so first thing, right? I can't believe I forgot to do this last time. DOU. Okay, so 2 times 10, right? Plus 2. We don't have any it's a hydrocarbon, right? So there's no oxygens, no halides, right? So and then there's 14 hydrogens, right? So 2. Right, so it's 22. 22 minus 14 over 2. So gives us 4. Okay, 4 degrees of unsaturation. Now, I'll give you a hint. Usually when you see 4 or more, that usually means a benzene, right? Because a benzene is, right, looks like this, right? You get 1 degree of unsaturation for the ring, and then 3 double bonds, so it's 4. So if this is above 4, 99 times out of 100, you're going to have a benzene ring associated with it. Okay? So, here we go. So let's start working on this, right? So, right, you notice how there's 1, 2, 3, 4, 5, 6. 6 signals, only 10 carbons. That means we're either going to have some covered up with no hydrogens on them, or there's some symmetry in the molecule, or both. So just be careful. But notice there's 3, 6, 3, 5, 8, 10, 12, 14, right? So all of these account for that hydrogen, right? So all the hydrogens are at least, there's some, so we can at least count for all of those, okay? So that's good. Nothing weird's going on. So, okay, so let's start working through this, right? So we know that this is, right? So so you start looking here, right? So it's CH3, right? Because the hydrogen, right, within the integration here, right? So that tells you how many are on that carbon, right? So it's a CH3, right? And then this says what's next to it. Remember the n plus 1 rule? N plus 1 equals the splitting pattern, right? Okay, so if we're going to triplet, that means this is 3. So how many neighbors plus 1 equals 3? Well, then it must have 2, so CH2. Okay. So for this one, right, so you have a CH2. But when you see this something of something, that means you have something on one side and something on the other. Okay, so this triplet would indicate, right, so triplet equals something plus 1, right? That something would be, you have a CH2 on this side, right? So on that side, right? And then something on the other side, the quartet, meaning you'd have 4 there. So what plus 1 equals 4? Well, that would be a CH3. Right, so you have a CH2 in the middle, with a CH2 on one side, and a CH3 on the other. A triplet of quartets. Okay, so for here, right, you have a CH3, right? And then, since it's a singlet, right, it would be what plus 1 equals 0, or excuse me, what plus 1 equals 1, right? It would be 0, right? So there's no hydrogen on that. For the here, right, so you have a CH2, right? It's a triplet, right? So that means, right, so what plus, what plus 1 equals 3, well, that would be a CH2. Okay, this one here, right? So here you have, again, CH2, right? What would be next to it? I'll double it here, so what plus 1 equals 2, right? So it would be CH, right? Same thing down here, CH2, CH, right? So you can look at those. Okay, now don't forget to look at the splitting, at the where the chemical shifts are telling you too. Okay, so what is this? So what are these? What do these indicate, right? So, again, I'm going to give you this chart. So something right around 1, that means just like a regular alkyl. Something, not a whole lot going on, right? So this is probably just CC, right? So along with this guy too. So that's right in this range of a CH2. So both of these are probably just regular CC bonds, right? But this one here, about 2.5. If you look down, okay, so it's not quite there. It's not next to a ketone, right? Because we don't have the oxygens, right? But it could be right in this range, right? Aromatic methyl, right? So it could be this one where there's a benzene. It's attached right next to a benzene. So this, right? So this CH3 could be attached to a benzene. Same with this one too, right? So benzene C, right? So it's right in that range, right, of the aromatic methyl. Okay. So by this, now these guys, this is in the fingerprint region at right around 7, would be right in here, right? Where is it? Right in with the arrow, okay? In the 6.5 to 8 range, right? So these are part of a benzene. Okay. So those are your benzenes. So how are we going to do this? You don't have 2 hydrogens, on a benzene, right there. Each carbon has it. Well, so what happens is with this, what's going on is you have your benzene, right? You have your hydrogens. Right, so I'm going to draw it like that. But you have something down here. So if you have it split like this, what's going on are these two are equivalent to each other. Sort of, if you think about it, if you're holding it this and sort of spin the ring, like you take a quarter and kind of spin it like that, it kind of spins. That's what you sort of see how these two are equivalent and these two are equivalent. Okay, but so they would integrate to 2 hydrogens, right? Because it's the same, it's one signal. But the only neighbor this one has is this one, and this one only has one neighbor, right? So it's almost like 2, right? So this would split into a doublet, and this would split into a doublet. But since they're basically equivalent, those doublets are right on top of each other. Okay, so these give one signal, these give another signal. So whenever you see this 2 hydrogen the set of two hydrogen doublets in this benzene rings, you've got this positioning here. Okay, it's called the pair. Let's call it the pair orientation, the 1-4. Okay, so like that. So that means we have something up here and something up here. Right. So what do we have? Okay, so what we have, right? So the first thing we look at, so this one, right? Notice that there's no carbons there, or no hydrogens there, and there's no hydrogens there, right? So most likely what's going on here is this CH3 is coming down here. Okay, so you have a CH3 here, right? It's right next to the benzene, right? The chemical shift would tell you that. But again, there's no hydrogens there. This one would also say that there is the chemical shift would indicate that this is a CH2. This CH2 would be right next to the benzene, right? But on this side, right, it's next to another CH2, right? We figured it out there. Okay. Now, what do we have, right? So we have this one here, right? But so we have this one, and this one taken care of. Well, what about these two? Well, we have a CH3 and a CH2, right? So what can happen is if we put the CH3 group there, right? It has to be at the end of a line, right? So that's the only place we could put it, right? But does it make sense? Well, we have a CH3 next to a CH2, and then we have a CH2 with on one side we have a CH2, on the other side we have a CH3. These guys here are fairly far away from here to not feel much of the effect. I'm feeling it a little bit, but not much, right? But these two, right, right where we need, right about 2.5, right, right next to the benzene, right, and these two guys, right, are right on the benzene. So this is the structure. So you have a methyl on one side, you have a purple group on the other. something like that. So that's how you go at, right? So there's start working through these things, right? Get the DOU, start thinking about the integrations, right? To tell you what's on the carbon, right? Start thinking about the splitting patterns, right? To tell you what the neighbors are doing, right? Remember, it's n+1, okay? And then also figure out what the chemical shift information is going to be. Again, I'm going to give you all the chemical shift information. I'm going to give you the IR chart. You're going to just need to know how to use it. So good luck, and we'll finish this up on Monday for our test on Wednesday. So, thank you.